Assalamu alaikum. So today we'll discuss the closed loop control of DC drive with a chopper. Now, and simply, if we discussing the speed controller for a DC machine, and let's assume this is omega reference, and we will compare it with the actual omega, then the error will go through a PI speed controller, and here we have the torque reference, which also proportional to the I reference. So we can assume that the output of the speed control either a torque or a current. Recall that the relation between the torque and the current is proportional, so the torque is proportional with the current at constant flux. So this means that if we have a torque reference, we will have a current reference. So let's assume that this is a current reference. So if we compare it with the actual current, then the error will go through a controller, current controller, and after that this will go to the converter, let's say here, and the converter will feed the machine. Let's assume here we are measuring the speed using tacho generator, and let's assume that we are measuring the current using current sensor here. So simply now we have an inner current loop. This is an inner current loop, and we also have an outer speed controller. So this is the inner current loop, and the overall this is the speed loop. So this is speed control. Now the combination between the controller and the converter in the case of the DC drive with the chopper. Now this is the error signal. So here IA reference minus IA. Here we have a controller, a current controller. Now the current controller will give the control command, let's say VC. After that we'll have the logic and the gate drives. So let's assume this block is logic and a gate drive. And this will give the gate pulse for the chopper. So here we are having the gate pulses that will go to the chopper in order to achieve the desired voltage. And remember, the chopper has an fixed input DC and it has a variable output DC according to the duty cycle. So here is the output. So simply we need to have a mathematical model that represents this system. And this is the only difference between the DC drive controlled by a chopper and the previous chapter, which was the controlled rectifier DC drive. In that case, here we have a controlled rectifier. Now we have the chopper. We have here a current controller. Until now it can be linear or non-linear. And here we have a logic and gate drive. Simply this is very important because if we compare the power from this side, this is a low power side, and this side is the high power side. So simply we need to isolate between them, and this is the idea behind the gate driver here. The gate driver will isolate the control side, which is the low power side, from the high power side, which is the converter side. Now for the current controller, in general we have two options. The first one is to use a linear controller, which is the pulse width modulation based controller. So the first one is to use the pulse width modulation or what we call the PWM controller, which actually a linear controller. So this one is linear controller, and the most common one is the PI, current control. The second choice is to use a hysteresis controller, or sometimes we call it the bang controller. This one is on-off control, which is a linear controller. So this one is non-linear which is on-off controller. So if we need to mathematical model the current control with the logic and the gate drive with converter, the first thing we must decide the used current controller, and we have two options. The first one is to use the pulse width modulation based controller, which is a linear controller, or to use the hysteresis current control. So first let's discuss the two quadrant. So if you recall here, for 2-quadrant chopper, if we replace it here, this is the first switch, this is the second switch. Each switch is occupied with anti-parallel diode, and here we are connecting the machine. So this is the 2-quadrant chopper, this is the plus minus VDC, this is the switch number 1, let's assume. The switch number 2, let's assume this is the D1 and this is the D2. Let's assume that this is the positive sense for the current IA, so this is the plus here. So remember that this is a leg, and we have one condition, that S1 plus S2 must equal to 1, which means that only one switch is active at a time, otherwise it will cause a shoot through or short circuit across the supply. So this means that the upper switches, the upper switch and the lower switch should be complementary. And simply in this case, let's discuss the pulse width modulation based current control. So here we will discuss first the pulse width modulation. So here, this is the IA reference. If we compare it with the actual current, then here we will use a PI current control. So this is a PI controller. Now this will give the command signal VC. Now here we will compare it with a carrier. And according to the comparison between the control signal and the carrier, we will generate the gate pulse for switch S1. Remember that switch S1 and S2 in complementary form, so if we taking the inverted version of the S1 switch, we will get the gate pulse for the lower switch, which is the S2. Now the gating here, so S1 is equal to 1 if VC is greater than V triangular, and 0 if VC is less than the carrier signal. So here in this in the pulse width modulation controller, VC is compared with a carrier, which is a triangular signal, and according to which one is higher, if VC, if the control signal is higher than the carrier, the triangular, then the switch will be on, and if the carrier signal is less than the triangular, then in this case the switch is off. So if we here plot the waveform, let's assume that this is the carrier, which has certain frequency and amplitude, and let's assume that this is the control signal. Here I'm projecting the intersection points in order to help us to plot the gate pulse. Let's assume that we will start from this point, and here this is the VC, and this is the V triangular, which has certain amplitude and frequency. Now let's compare between this point to this point. V triangular is greater than VC, then the gate pulse will be 0. Between this point and this point, VC is greater than triangular, then the gate pulse of S1 will be 1. So here I'm plotting S1 gate pulse, or sometimes what we call it the Q1 gate pulse. And between here and here, VC less than the triangular, so the gate pulse is 0. After that, between this point to this point, VC greater, then the gate pulse is 1, and so on. So this is how the gate pulse is generated. If we need to plot the gate pulse for the second switch, which is the S2, this is the complementary. So if S1 is 0, then S2 will equal to 1, and if S1 is 1, then S2 will equal to 0, and this will continue in the same scenario. So this is how to generate the gate pulses for the upper and the lower switches. If we need to plot the output voltage, now VA will equal to VDC when the S1 is on and 0 else. So it will take the same waveform as the switch Q1 gate pulses. So this is actually the V out. From the chopper. So simply here, the chopper frequency is fixed by the triangular waveform. So we can write here that the chopper switching frequency is fixed by the frequency of the triangular, by the frequency of f a triangular. So this waveform has amplitude and has a frequency, and here the switching frequency is fixed by fixing the frequency of the triangular, and simply the frequency of the triangular will decide the bandwidth of the current control, and this will decide the bandwidth of the current control, which means how fast that the current control can go. So the bandwidth of the current controller is limited by the F triangular, which means the speed of the current control, or the time constant of the current control, cannot be faster than the carrier frequency. This is very important. Now we know that the duty cycle, or the duty ratio of the chopper, is actually T on over the period. And here, because we are doing a pulse width modulation, we are cutting slices, we need to find an average value for the duty cycle. So here we can write that the duty cycle of the chopper can be, let's fix this one. Which is the D equal 1 over the period of the triangular, the integration from 0 to t plus t triangular, d dt, or let's assume this is q dt, and here we have the t from t to t. So this will equal the integration 1 over the t triangular, the integration from 0 to t triangular, q dt. So d will equal the t on of switch 1 over t triangular. And we know that if we need to calculate the average value for VA, it will equal D multiplied by VDC. So simply this means that the chopper can be seen as a variable voltage source with average current control. This is the pulse modulation based control. What about if we need to have a hysteresis current control, which is the second option? So the second current controller is the hysteresis current control. We say that this current control is a nonlinear current controller, and it's on-off or bang-bang current control. So how the hysteresis current control is working, let's assume that this is the reference current. The first thing, we will draw an envelope or a window above and lower the reference current with delta IA, which is the maximum allowable ripple in the current, which can be also related to the ripple in the torque. So this is the envelope. Let's assume that this is the envelope. So the envelope here, between here and here, has delta IA length, and the same thing here is delta IA length. So I'm having an envelope above and lower, or up and under the reference current. This is the IA reference, which decide the maximum variation or ripple in the current, and we will decide for the gate pulse according to the following relation. If IA is less than or equal IA reference minus delta IA, which means that I am under the envelope. So I should put the current inside the envelope as fast as possible, which means that I will impose all the voltage that I'm having, which means the gate pulse should be 1. Now, if I'm hitting the envelope or the current is out from the envelope, which means that IA is greater than or equal IA reference plus delta IA. In this case, I need to cut the power from the machine, which means that I need to switch off the switch. So the switch will equal to 0. So let's see how this can be done. Let's assume the current was here. So if the current was here, and let's try to plot it, and let's assume that we are starting at this point, plotting. Now the current is under the reference current minus the envelope, so I need to impose all the voltage that I'm having, which means that I will impose a gate pulse 1. So logically this means that the current will increase. Let's assume the current will increase until hitting the boundary here. Hitting the boundary, I will not do nothing because I am here, which is IA is equal to IA reference minus delta IA. Still the gate pulse will equal to 1, and this will rise the current until, let's assume, it's hit the boundary at this point. So now at this point IA is equal IA reference plus delta IA, so the switch must equal to 0. So now from here to here is 1. After that the switch should go to 0. So the switch goes to 0. This means that the voltage is reduced, so the current will reduce. So let's assume that the current is reduced and it hit the boundary at this point. Now hitting the boundary here, now I am in IA is equal to IA reference minus delta IA, so I must turn on the switch. So the switch will be turned on here. Now this will cause the current to increase until hitting the boundary. Let's assume it's hit it here. So at this point IA is equal to IA plus delta IA reference, so I must turn off the switch at this point. So the current will be reduced. Let's assume it reduced here. Now I will judge only on the boundary. So at this point I am in the IA minus delta IA reference, so the switch must go to on. And the last one, let's assume it hit the boundary here. So now this switch is on until this point. Now at this point I am in this boundary. IA is equal to IA reference minus delta IA, so the switch will turn off. So simply this can be implemented as a comparator, which is IA reference minus IA. This will be the error, I error, that will go to the band controller, which decide the error, and after that we are getting the gate pulse, which is the Q1 for switch S1, and the complement value for this one is the S2 gate pulse. So simply here we can note that the switching frequency here is not fixed. So simply here we can say that in this kind of controller the switching frequency is not fixed. However, for the hysteresis current control, we have instantaneous current control, very fast current control. So this actually is an instantaneous current control. And the current is controlled within a narrow band. Let's say here we can say that the current is controlled within a narrow band, of the desired current or IA reference. And the window, the hysteresis window, will decide or the maximum deviation of the IA or the maximum ripple allowed in the torque. So the hysteresis band or what we call the window determines the allowable ripple in the current. And you know that this will also has a relation with the torque ripple. Now if we compare the pulse width modulation based control and the hysteresis based control, we can have the following characteristic. So let's assume that this is the hysteresis. Controller, and this is the pulse width modulation controller, Now we will compare, let's assume, the following characteristic. The first one for the switching frequency. Now we notice that in the hysteresis current control, the switching frequency is not constant, so it's varying. While for the pulse width modulation is fixed by the frequency of the triangular, so here it's fixed. The second performance index, let's say the switching losses, now for the pulse width modulation, it has a low switching losses. Of course, if the switching frequency is high. However, in the hysteresis current control, the losses is high due to the varying switching frequency. Now, the speed response for the hysteresis current control, it is instantaneous current control, so this is the fastest. For the pulse width modulation, it's also fast, but the hysteresis is faster. For the ripple in the current, or current ripple, now for the pulse modulation, it's fixed. For the hysteresis, it's adjustable by adjusting the window. So this one is adjustable. Which depends on the hysteresis window. Which is the delta IA. Now for the filter design or filter size, now for the pulse modulation, it's small, and for the hysteresis, it will depend on the delta I. Now, most of time in the literature and the industry, we prefer to use the pulse width modulation type controller. It's linear, it has a fixed frequency, it has a fast response, low switching losses, and simply it has a small filter size. So this one is the preferred method. So if we return back here in the first question, so if the current control is hysteresis, the only design requirement is to specify delta I, and this will end the design, simply because this one will become a linear controller, and the only thing that we can design here is the window length that will decide how much ripple is allowed in the current or how much ripple is allowed in the torque. But in the If we are using a pulse modulation, in this case we need to find a transfer function, and after that we'll use our tools from the linear contour theory in order to design the overall controller, and this will be our topic in the next lecture, inshallah. Assalamu alaikum.